So we're trying to find the particular solution to this ODE for the damped-driven harmonic oscillator. And you remember from the last lecture that finding the particular solution is basically an exercise in guessing the right thing. So you might think that, okay, maybe I should try to match the right-hand side, which is something like, you might try guessing something like this. X is A cosine of omega d times t. That might be your first guess. But that's not going to work. You can see why, because if I take the derivative, I'm going to get a sine, right? And then there would be no other term with a sine in it. So this term would have cosine, this term would have cosine, this term has cosine, so that looks pretty good. But then this one has a sine in it, which doesn't match anything else. And so I'm not going to be able to solve that ODE. So this is not going to work, actually. You might try to make your guess a bit more sophisticated. So you could start trying to make it refine it a bit, add a phase here, which is equivalent to adding a sine, cosine of omega d times t plus b sine of omega d times t. So you could try guessing something like this. So now when I take the derivative, I get sines and cosines in both terms. And so all the terms have a sine and a cosine. This actually will work. It will work, but, works. However, it's ugly. I'm just going to tell you that if you try it out, the algebra gets pretty terrible. So if you want to, go ahead, try it with this, and you can test to see that you get the same answer that I get at the end of the day. But instead, what I'm going to do is the method that I advocated in the last lecture. So a better way is to complexify the ODE. So I'm going to complexify my ODE. I'm going to instead look for a complex function z, p, particular solution, which is going to be some xp of t plus I yp of t. So I'm imagining I'm looking for some complex function. And the thing I actually want is this, which is the real part of z. So xp, my target, is the real part of z. And then I'm going to take my cosine and I'm going to change it into a complex exponential. So I'm going to take e to the I omega d times t is equal to cosine omega dt plus I sine of omega dt. So with that in mind, if I instead can solve this equation, z double dot plus gamma z dot plus omega 0 squared z is equal to f0 over m e to the I omega dt, I can get my answer. And the reason you know that's going to work is because if I take the real part of this equation gives us our original equation. So if I take the real part of this equation, I get my original equation back. So if I can solve this equation with the z and take the real part, I'll get the solution to my original equation. So the plan for this complexification, just to review, is to one, solve for z. Sorry, slipping into American. Solve for z, and then take the real part to get x. Sorry, I should say solve for a particular solution zp, take the real part to get xp. So that's what we're going to try. Okay, so we're trying to find a particular solution to now this complexified ODE. And this, we've seen how to do this, because there's an exponential on the right side, and exponentials make everything easy. So we'll guess zp of t is equal to some amplitude a e to the I omega dt. So let's guess this, and then let's plug it in. So those are the derivatives. Derivatives are very simple when it comes to exponentials. I could just bring a factor of I omega d down each time I take a derivative. And let's plug it into the ODE. Well, there you have it. Plug it in. And that great thing happens. You know you're on the right track every time this happens, that every term has an e to the I omega dt in it. So I can cancel them out. Time dependence is completely gone. And I can solve this for a. So I group together some terms, and then let's just divide and solve for a. And there you have it. So we found a particular solution to z, right? We guessed this, and we found that we were able to solve the ODE if a is equal to this. So we have a solution to the complex equation. One thing that's important to note is that a is complex. Notice that there is an I sitting here. So that's a complex number. And that's going to be important going forward. Okay, but step one of the plan is done, and that was pretty easy. Now we need to go to step two, which is to get the particular solution to x, which was our ultimate goal. I need to take the real part of Zp of t. And it's not so simple because I have an I sitting in a, so a is a complex number, but then there's also an I sitting up in the exponent there, up here. And that makes calculating the real part is a little bit of a pain, but not too bad. We'll show you the most efficient way to do it. Okay, so we have our solution for the particular solution of the complexified ODE, and now we just have to take the real part to get the thing that I was ultimately looking for. Okay, now the problem is a is a complex number, but let's use this to make our life a little bit simpler. So a is complex, so a can be written in terms of a magnitude and a phase. So let me write a, which is a complex number, as a magnitude, e to the I times a phase, okay? And just by convention, I'm going to call that phase minus delta. So this is convention, is the phase of A is defined to be minus delta, okay? That's just a definition of that constant, okay? So it's a complex constant, it's got a real part and an imaginary part, or you can write it as a magnitude and a phase, or modulus and a phase. So let's make use of that. Zp of t is the magnitude or the modulus a, e to the minus I delta, e to the I omega d times t, which is equal to the modulus of a, e to the I omega d t minus delta. And now, you can see why I wrote it that way, because this is Euler's theorem, which I can use very easily. This is cosine of omega d times t plus I sine of omega d. Whoops, plus minus delta. I got my minus delta. Minus delta plus I sine omega d t minus delta. Whole thing times a, like that. Okay. So what's the real part of Zp? The modulus, remember, is real. So that thing out in front is a real number. And here's my real part. And here's my imaginary part. So the real part of Zp is just the magnitude, a, times cosine of omega d times t minus delta. Okay. So now I know how to get my particular solution for x, I take my a, find the modulus, and multiply by this cosine. So this is all schematic now, right? We have the solution. Is known schematically, but I have to fill in the details. So we still need, I need to know what is the modulus of A and what is delta. Okay. I need to know these in terms of all of those things that I can control: F0, omega d, omega 0, and gamma, and m. So I need to fill in those details. But once I know A and delta, I will know this particular solution.